All right. So a couple of items right off the bat here. So I'm going to do something kind of interesting with the test. I know I'm going to be gone on Thursday and Friday. You may or may not remember that I said that, but I'm going to be gone Thursday and Friday. I will kind of pre-record a lecture for one of those 2 days. One of those 2 days, you're slated to have an exam. But the way the exam is going to work is that it will be take-home. Okay. Now, here's the thing. I will actually give you the table that I made that's kind of in the slides that has the test for series convergence on it. Okay. So there will be a sheet on the last page of the exam that has all of the tests for convergence on it. But other than that, you can't use anything. Okay. So there's no time limit in terms of how long it's going to take. It will be due on Monday. Okay. And the way that you will turn it in is either turn it in by hand here, like a paper version of it, although I will post the exam in Canvas, or you can snap pics of the various pages and upload it into Canvas. I'll make a sort of Canvas exam and give you the ability to upload files. And then you can take pictures and kind of upload those if that's convenient for you, or if you're unable to hand in a paper version of it. Okay. But again, you're on the honor system. The only thing you're allowed to use is the sheet that I will provide you with at the end. So I will pass that out, or I will kind of make that live on Thursday. And then the exam itself will be due in class on Monday. Okay? Yes, David.
So you were gone Thursday and Friday, and only one of them was going to be recorded lecture. One of them was going to be taken, but we're also taking it home. It's a take-home exam.
Yes. Yeah. So
we just not have class?
no, we will still have class on Monday. We're not having class Thursday or Friday. Yes, we will still have class Monday. Yes.
Thursday we'll just have that, and Friday we're going to have it recorded.
I will record one lecture for the totality of Thursday and Friday. I mean, there's just one lecture, and then one of those days we're going to have the exam, and I'm giving you more than just that day to actually work on the exam. Yeah. Yes.
Yes,
Well,
I think what he's trying to say is like on Thursday or Friday, we have to come into class.
no, no,
Okay.
no. You don't have to come into class on Thursday or Friday. No. But Monday you do. Okay. So start coming back to class on Monday for sure. All right. Is that clear? Yeah.
Will the material be the same?
Yeah. Yep. Material will be the same. Yeah. Basically, the focus will be on series convergence and divergence. Like I said, there's going to be one section of the test that's going to be just a straight up decision where you say, okay, this converges or diverges, and you simply articulate which test you are applying. But once you've used that test, the other ones in that section, you can't apply that test to those. Does that make sense? That's kind of a good, it's a good exercise, having to really kind of carefully use a test. You don't just get to use the limit comparison test on every single problem or something. So, but there are going to be other problems where you can do whatever you want, so long as it's valid, right? Other questions? Okay, so that's, again, I will record a lecture, one lecture for those 2 days, and then you don't have to come to class Thursday or Friday, but the exam I will post in Canvas on Thursday. Okay? All right. today, we're talking about hyperbolas. Okay, it's the third of the interesting conic sections. We had some sort of uninteresting degenerate conics that we cast aside very quickly. The interesting conics include parabolas, ellipses, which we talked about last time, and hyperbolas. Okay? These three things came up as different ways of slicing through a cone with a plane, right? A double napped cone, actually, with a plane. That's why it's called a section, because we're slicing through, yeah? Just kind of graphic, but you know what I mean, right? I'm slicing through this thing, seeing how a plane intersects with these double napped cones. And today, we are slicing through this thing and getting hyperbolas, right? If you go back, oh man, that's way back there now. Let me see. Go back here, it was this situation right here that was the hyperbola situation, right? So, okay, and this one, okay? So what's interesting is a hyperbola actually has two branches instead of just one, okay? Whereas all the other situations we've encountered so far, there's literally just kind of one thing. Here, there's actually two parts of it, okay? So that's something to bear in mind as we jump in here. Oh man, that was, okay, so here we go, hyperbolas. So I said that each one of these has a rigorous geometric description, and a hyperbola has one as well. And it's actually somewhat similar to what we had for ellipses, with one difference. There, we had two foci to begin with, and we said that a point xy is on the ellipse if the sum of the distances from the point to both the foci, the sum of those distances was a constant. The only thing we change for hyperbolas is instead of the sum of the distances, what do we take? The difference. The difference has to be a constant. So here's the thing. Really, I should put this difference symbol in absolute values. That's what's really going on here. Okay, so the absolute value of the difference between these distances from a point on the hyperbola to the two foci, that is a constant. And if I call this distance from the center, so the center is kind of weird. The center in this case is the point kind of in the middle between the two vertices. Okay, the vertices are these kind of points of symmetry for the hyperbola. That distance right here is called A. Okay, so unfortunately, everyone, Zoom decided to do a sweet update to their software, whereby every time I try to annotate, it like labels the annotation with whatever device is doing that. So we're just gonna have to gut that out. I'm gonna have to spend like an hour trying to figure out how to turn off that feature at some point because it's incredibly annoying. So we're just gonna have to sort of let that happen here, okay? But yeah, Zoom is the problem, but it's also a solution. So it's a paradox, I tell you, okay? So here we go. This distance from the center over to a vertex, that's what we call A, all right? And therefore, if I go up here, look, so for instance, this point right here is on the ellipse, that vertex, yes? That vertex is sitting right there that I just labeled in red. And if I go over to here, to this vertex, and then from this vertex over to the other focus, that has to also be equal to that whatever constant that happens to be. But how far is that? So like this distance right here is A over to that vertex. How big is that difference? Well, look, if right, so in this case, let me just kind of write this. This is D1, or I guess, This distance right here is like D2 or something. And this distance right here is D1. So what is D2 minus D1 going to be? D2 minus D1 equals, think about it. D2 is the distance from the focus over to that vertex, yeah? And then I subtract off D1. Well, that's just going to subtract off that tiny thing at the beginning, yes? And therefore, what am I going to get? Right, if this distance right here is A, okay, and I'm literally, if I subtract off D1, all it does is it gets rid of this part right here. Does that make sense? It's just going to get rid of that. And all I'm going to be left with is how many A's? Yeah, 2A. Right, there's another copy of A right there. Okay. So this difference is equal to 2A. Yeah? Kind of like what we found out with the ellipse. In the ellipse, what did we discover the sum of the distances was all the time? 2A, right? And what was A? A was, again, the distance from the center all the way over to the vertex, yes? From the center to the vertex was what we labeled as A, okay? C, once again, right? C, once again, just like it was in the case of the ellipse, C is the distance from the center over to the focus, yeah? That was exactly what C was in the case of the ellipse. But notice something. In the case of the ellipse, how were A and C related to each other, like in terms of their size? For an ellipse, remember we had two foci, yes? Here was the center. This distance from the center over to the focus, that's what we called C. And this distance all the way over to the vertex, that's what we called A. What was true about C and A as it pertained to the ellipse? C was smaller than A, right? What's true for a hyperbola? Bigger, yeah? C is actually going to be bigger than the distance from the center over to the vertex, okay? Okay, any questions on that so far? So again, the only difference between the ellipse and this is instead of looking at a sum of distances being constant, we say the difference of distances has to be a constant. And difference in absolute value has to be a constant. And that constant happens to be 2A, which is twice the distance from the center to the vertex, which is really the distance between what? The vertices, the two vertices of this thing. Okay. And that was also true in the case of the ellipse. All right, are we good to go on this? Kind of like the basic definition. Okay. Any questions? All right, the line segment connecting the vertices is called the transverse axis. Transverse axis. Okay, so there's one part of my ellipse like this. Okay, if I connect the vertices here, it's a horrible looking ellipse. Okay, and I kind of extend this out. This is called the transverse axis. Transverse axis. Okay. It's also sometimes called the axis of symmetry, but the transverse axis reminds us that this thing is actually kind of going through it. Yeah. It's like traversing through this thing. That's why it's called the transverse axis. Okay. The midpoint of the transverse axis, by the way, the transverse axis technically is just the segment that joins the vertices, but I like to think of the transverse axis as kind of continuing on. But technically speaking, it's just that segment, right? The line segment connecting those. The midpoint of that thing is called the center of the hyperbola, the center of it. And again, I already mentioned this, but one distinguishing feature of a hyperbola is that its graph has two separate branches. Okay. All right. Here is the standard equation of a hyperbola. And once again, this isn't very hard to come up with, actually. In fact, It's very similar to what we did in the ellipse case. You would have to go and use the formula for distance between 2 points, and you would have to capture that idea that the difference in those distances between points and the foci is equal to the constant 2a. And then you kind of play around with this thing. HK is the center. And when you rearrange stuff, you get something that looks like this. And what is B? What in the world is B? Okay, well, we'll talk about that. One thing that is true, and you can almost define B this way, B is simply, C squared. We know what C is, we know what A is. C squared is equal to A squared plus B squared. Okay, you can almost define B by the equation C squared minus A squared, okay, if you really wanted to. What was the formula relating A, B, and C for the ellipse? How were things different? You remember? What was C squared equal to? Yeah, the plus switched to a minus. And by the way, these two equations look very much like the ellipse, except what? Instead of a plus, we have a minus. It's not too surprising that lots of pluses are changing to minuses. After all, we've gone from a sum situation to a difference situation. Okay. Okay. And by the way, the A is always, okay, so like the way that this thing is written, A is always going with the distance between the center and the vertex, yeah? A is always the distance between the center and the vertex. So do you see that A kind of migrated from being underneath the X stuff to being underneath the Y stuff? Because I could have a transverse axis that's vertical, right? I could have a hyperbola that's oriented in sort of the vertical direction rather than the horizontal direction, okay? So again, the A is always the distance from the center to the vertex, and therefore it could be underneath the Y stuff as opposed to the X stuff. Does that make sense? Hopefully, yeah? These are the formulas, the standard formulas. If the transverse axis is horizontal, the A thing is underneath the X stuff, and the X stuff it doesn't have the minus sign attached. Okay, that makes sense. Okay, because for instance, think about it. If HK is the center, by the way, is the center a point on the hyperbola? No, the center is not a point on the hyperbola. Okay, but what is on the hyperbola apparently? So like in the case of horizontal transverse axis, if I go from the center and I go A units to the right from the center, right? To the right from the center or to the left, I should land on the hyperbola. Yeah? Okay. So let me just say that in this case, H and then K plus A and H K minus A are on the hyperbola. On the hyperbola, okay? And are they? Let's check this out. Actually, hang on a second. I think I wrote these things wrongly. Shouldn't be H. I don't add things to the y-axis. What would I add if I was horizontal? What would I be adding? I would be adding to the x-axis, or to the x-coordinate. Sorry, so it should be H plus A comma K. That would be on there, and also H minus A comma K. Right, so I would add and subtract A units from the x-coordinate, not the y-coordinate. I would add and subtract A to the y-coordinate if I was vertically oriented. And so check this out. Do these work? Does this particular point actually satisfy this equation? Right, I would take this H plus A and I would plug it in for X, okay? And I would plug this value in for Y, And I had better get that equation being satisfied, yes? But if I plug in x equal to h plus a, what happens to the h's? If I plug in x equal to h plus a, what happens to the h's? They cancel and you're just left with a. So you get like a squared over a squared minus, okay, what if I plug in y equal to k? What would that be? 0 squared over b squared equals 1. Is that true? Yeah, that is true. So that is clearly a point on the hyperbola. Just like if I were to add and subtract a from k, in the second case, I would end up with something on the hyperbola. Does that make sense? Okay. I just basically checked to make sure that the vertices were on the hyperbola. This and this are the so-called vertices of the hyperbola. Vertices. Okay? All right, any questions on that? We have the standard equation of the hyperbola. A is always the distance from the center to the vertices. And b squared is kind of defined in this silly way right here. C squared is equal to a squared plus b squared, but that shouldn't be a big surprise to us because of our work with ellipses, okay? And we will see more practically what b is here in just a minute. But any questions on this so far? A is the distance from the center to the vertex. C is the distance from the center to the focus, yeah? C is bigger than A. B is this mystery quantity. What in the world is it? Well, we'll see here in just a minute, okay? What was B in the case of the ellipse, by the way? A was the distance to the vertex on the major axis, the one that had the foci, yeah? A was the distance from the center to the vertex. What was B? The distance from the center on the minor axis up to the top, yes? It was that distance instead, okay? All right. So this is actually what B ends up being is in this picture right here. You have things called asymptotes for the hyperbola. These are lines that kind of trap the hyperbola, and the hyperbola gets closer and closer to these lines as x and y get bigger and bigger and bigger, okay? And if you draw the asymptotes and you draw this box that has, you know, these points on it, or the vertices on it, and then you go up to the actual asymptotes like this, and you draw this box, like you can basically see what B is, okay? B is this thing right here, okay? So B is the actual distance from the vertex up to the top of that box, okay? So in other words, this box right here, what are the dimensions of this box? Well, the 2A in this direction, and in this direction, it's 2B, okay? And of course, we have the center right there, right in the middle, okay? C, okay, therefore, where's C in this picture? Where do you think C is? Because remember, C was the distance from the center to the focus, correct? So where is C? Yeah, Michael. Yes. Yes. Amazing. It would be from the center to the corner right here. So that's what C would be. So here's what's amazing. You know that the focus, I don't know, is like right here or something, correct? So this distance is also C, which tells us that what's going on here, oh man, I'm going to mess my picture up here, but you know, which tells us that if I were to draw a circle of radius C, that circle would actually pass right through that corner of that box. Does that kind of make sense? Okay, so if I were to draw a circle, and I'm not going to ruin it for you. This is a sweet geometric exercise. Okay, well, I showed you how to do the one in the case of the ellipse, right? It kind of was the relationship between A, B, and C, and there was some nice right triangle stuff going on. The same thing happens here. So think about it over in Chuck's or, you know, Chick-fil-A or Tossed or whatever, you know, draw some pictures and try to figure out why this distance has to be the same as the distance from the center to the corner. You could easily see that C squared is equal to a squared plus b squared now, right? Because after all, this is a right triangle for crying out loud. Yeah. Okay. Okay. Cool. Any questions on that? We'll talk more about the asymptotes and what they actually are here in just a minute, but just wanted to point this out. Okay. So any questions on that? I think that's a pretty cool little box looking thing. Okay, that's C right there. Here are the asymptotes. You might say to yourself, what is going on? Okay. What is going on here? Well, a lot actually. Now, what was the formula for the horizontal transverse axis ellipse? Well, wasn't it like x minus h squared over a squared is minus y minus k squared over b squared equals 1? Remember that? Okay. Well, so if x and y are huge, okay? So suppose, I mean, look, I can, like, it, in theory, in this equation, x and y could get really big. Do you understand? Like x and y could get huge, and that difference could still be made equal to 1, yeah? So in other words, these guys right here, x and y, those things could get huge, okay? Exclamation point. And would there be very much difference? So like, think about it for a second. Basically, what would be going on is you would have this difference of these giant numbers. And in the end, how far apart are they actually? According to this equation. So like I would have this huge number that was trillions big from the x part. And then I have this other huge thing that was trillions big from the y part. And I would take the difference, and that difference would be 1. What does that tell you about these two quantities right here? Well, it tells me that they're not that far apart from each other. Does that make sense? In fact, we know how far apart they are. They're 1 apart. And in fact, the two things, like, what would you be able to say about the ratio x minus h squared over a squared and this other ratio y minus k squared over b squared? How close would that thing would be? Almost basically, right? If x and y were huge, that ratio would be how much? Those numbers would be almost indistinguishable from one another. They're only 1 apart, you understand? Well, each one is like trillions large. What would that ratio would be really close to? 1. So that, my friends, is where the asymptote comes from. Because look at this. That means that basically what we have is that x minus h squared over a squared is equal to y minus k squared over b squared, right? Those two things are almost equal to one another. And so what you can do is take square roots. But you have to be careful when you take square roots, right? Because you have two sides that are squared. So that means the one side could be negative and the other one be positive, and then in squaring them, they're the same, yeah? So if I take the square root, right, if I take the square root of both sides, what am I going to get? Well, basically, you're going to get that y minus k quantity squared over b squared, or sorry, hang on, not squared anymore. If I take the square root, what is it going to be? Y minus k over a is equal to, now I have to be careful, it's equal to x minus h over a, but I have to allow for pluses and minuses. Do you see what I'm saying? This would be equal to plus or minus x minus h over a. Or sorry, sorry, I have an a over here, but what should this be? This shouldn't be a, that should be b. Does that make sense? So that tells us if I multiply through by b, that y minus k is equal to plus or minus b over a times x minus h. You see that? And another way to write that is what? Y equals k plus or minus b over a x minus h. And again, up here, this was an approximation, but what I did is I just kind of basically said, well, what if those were equal to each other? Well, and I get these equations right here, which are exactly these asymptotes. Do you see it? So the way that you get these asymptotes is basically by ignoring this one right here. You can kind of ignore this one and put a 0. And that's essentially what's going on. You're kind of putting a 0 there and you're saying, look, they're basically the same. Come on, right? I mean, they're billions or trillions large, and they're only one apart. They're basically the same for all intents and purposes. So that's where the asymptotes come from. Basically, what you're saying is y, for x and y huge on the hyperbola, y is basically either k plus or minus b over a times the quantity x minus h. Yeah? That's how y is basically determined here. Does that kind of make sense? That's where these asymptotes come from. Okay. And by the way, the only thing that changes in the other case is that instead of b over a, you have a over b. Or you can kind of solve for x in terms of y if you really wanted to. But I think this is a better way to think about it, having a over b instead of b over a. Okay? So those are the asymptotes for the hyperbola. All right. Any questions on that? Questions? Okay, here's the picture. So the asymptotes coincide with the diagonals of the rectangles of dimension 2a and 2b, because look at this. What is, what is the equation of, like these lines? Well, so like this line right here, I'm telling you is going to be y equals k. I think this one is plus b over a x minus h. X minus h, okay? Another way to say that is y minus k over x minus h is equal to b over a, okay? Is equal to b over a. That means the slope of this line is b over a. Okay, so that's the one asymptote. The other asymptote, of course, is y equal to k minus b over a times x minus h. Okay, so those are the two asymptotes. Okay, just wanted to kind of drive that home. All right. Why don't you go ahead and work on this for a couple of minutes? Okay, let's take like 5 minutes and work this one out. And you can tell me what you come up with. You're going to want to put this into the standard form and tell me whether this thing is oriented horizontally or vertically and all that good stuff. Okay, so take a couple of minutes and check that out. Right, so the first thing we do is we divide by 16. We get this. Yeah? So what is the center? 0, 0, the origin. Yeah? What's A? So in other words, HK is equal to 0, 0. What's A in this case? 2. B? 4. Okay. So what are the asymptotes? Remember, it was like y equal to k. Again, and this was a horizontal transverse axis, yes, because the x stuff has the positive sign on it, yeah? So it's y equal to k plus or minus b over a x minus h. That's the generic form. But what's interesting here is that h and k are both 0, yes? So if I do b over 2a, what do I get? 2. So the asymptotes are y equal to plus or minus 2x. Those are the asymptotes, yeah? Those are the asymptotes for this thing, the asymptotes. And that I actually like to think about the asymptotes and have that help me sketch things, because once you have the asymptotes, you can actually sketch the box. If I go back to the previous slide, that box kind of tells you where the vertices are, yes? And once I know the asymptotes, it's easy to come up with that box once I know what A is, yeah? But of course, to draw the asymptotes or to write down the equation of the asymptotes, I will know what A is, yeah? And B is just the distance. If I go over A units from the center over to the vertices, B is just that distance up to the top of that box that's, you know, trapped inside of the asymptotes, okay? All right, so the transverse axis is horizontal and the vertices occur at -2, 0, and 2, 0, okay? And the ends of the conjugate axis, okay, the conjugate axis is the one that's flipped this vertically. Does that make sense? It's the one that's perpendicular to the transverse axis. Conjugate axis is the other one. In this case, that's vertical. You go up and down by B units, okay, to get that thing, okay? And here's the picture right here. Okay, here's the picture of things. So you kind of draw this box. You could also just draw the asymptotes, right? The asymptotes are right here, okay, and right here. Oops, that's not very good, but you know what I'm saying. So this is y equal to 2x, and this is y equal to -2x from the previous slide. And then it's easy to draw the hyperbola from there, yeah? You kind of go to the vertex and you get the hyperbola that way. Here it is, here's the result, sitting right there, yeah? Okay, so that's interesting. Okay, any questions on that? Yeah.
Why do you would you want us to find the asymptotes before you find like the ends of the conjugate transverse axis? Because like in geometry, I was taught like you just connect the corners of the box and then you have the asymptote.
Yeah, I don't know. I mean, you could do it that way or the other. If you do the transverse or conjugate axis and get that box, you know the asymptotes. If you know the asymptotes, you know the box. I mean, you can kind of go either direction. I just tend to want to find the asymptotes real quick. That's going to involve finding A and B in the center. Does that make sense? But you know, you could do it the one way or the other. It doesn't really matter. Okay. All right. Other questions on that? Okay. Eccentricity. Remember, eccentricity for the ellipse meant squattiness of like the ovalness of the thing, yes? And the eccentricity in the case of, eccentricity in the case of the ellipse was always between where and where? What two numbers? 0 and 1, yeah? Okay. And what did we do? We took the distance to the focus and divided by the distance to the vertex. Same thing here. Make sense? Okay. But what did we notice about the relationship between C and A in the case of the hyperbola? It was flipped around, yeah? In the case of the ellipse, C was smaller than A all the time, yeah? In the case of the hyperbola, C is always bigger than A, so the eccentricity will always be bigger than 1, okay? Now, what do you guys think is going to be true? What should we consider to be eccentric for a hyperbola? Okay, so like the closer we were to 1 in the ellipse, what was going on? The closer that we were to 1, the closer the thing was, or no, hang on a second. The closer we were to 1, the more ridiculously oval shaped it was, yes? Okay. the closer the eccentricity was to 0, the closer we were to a circle, yeah? Okay. So, so what's going to be eccentric? What does eccentric mean here? Because it looks like we have a quantity that's always bigger than 1. And it seems like probably being close to 1 or really big are going to be the two extremes, yes? Either really big or really close to 1 from above are going to be the two extremes. So what does eccentricity mean? Okay, well, eccentricity of a hyperbola is that thing, because c is bigger than a, the eccentricity, which by the way is equal to c over a, is always greater than 1. If the eccentricity is large, which means big eccentricity, okay, what does that mean? Well, it means that you have a really kind of like, I don't know, vertically looking hyperbola. Okay, it almost looks like two parallel lines in some sense. Yes. Okay. So that's large eccentricity. If the eccentricity is close to 1, what do you have? Well, that means the vertex is really close to the focus. Yes. And you have a really like a really squatty looking hyperbola. Does that make sense? So I guess that would be small eccentricity, but that's just eccentricity close to 1. So eccentricity large means that the branches are almost vertical or something. Or if it's in the other direction, the branches are almost horizontal. Okay. If the eccentricity is close to 1, that means that thing is really kind of pinched. Yeah. You really have a pinched hyperbola. Okay, so that's kind of an interesting, somewhat of a departure from what was going on with the ellipse situation. Yeah. The more pinched the thing is, the closer you are to 1. Okay. Although I guess like the squatty oval thing in the ellipse, that what was true there? We were close to what? To 1. If you're close to 1 with your eccentricity with hyperbola, you're going to have a really pinched thing too. Looks like an elephant sat on this thing. Yes. So same sort of thing. Elephant sits on the thing, you're going to have an eccentricity close to 1. In either the case of the ellipse or the case of the hyperbola. Does that make sense? Okay. A big eccentricity means that this thing is almost like 2 vertical lines or 2 horizontal lines. Okay. Make sense? Hopefully that makes sense. Okay. I think that's it. That's all I have. We know everything about the conics now, and we're going to start doing some calculus with them tomorrow, for sure.